Hello, we are in Digital Electronics Lab and today we will discuss about the logic gate ICs. Okay, we will perform some experiment and we will study that how this logic gate IC we can use in our practical applications. Okay, but before that we will take a quick review that of that how the ICs are working using the transistors. Okay, this is because the basic building block of these ICs are transistors, and nowadays the CMOS technology has been widely used to develop this kind of ICs, but we will take an example, a few examples to develop these ICs using the BJT, that is bipolar junction transistors. Okay, then you will see the internal diagram of that particular ICs. Okay, and then we will go to the table and we will verify these ICs. Okay, and by this experiment, if we don't have the IC testers, with this kind of experiments we can easily verify a particular IC, that whether this IC is working properly or not. So if we don't have any IC tester, this experiment can be helpful. So that we can easily study these ICs and we can easily understand that whether these ICs can be used in practical application or not. Okay, so before going into the table, let's take a quick review that using transistors how we can build this kind of ICs. So we'll draw the symbolic representation of a transistor and we'll see that how this transistor can be used as a NOT gate. Okay, so this is a symbolic representation of a transistor. This is the symbolic representation of the transistor. So this is emitter, this is base, this is collector. Okay, but what happens in case of transistor, if we apply any input over here, then this transistor is switch on. Okay, so whatever current is there, it can be passed through it. So if there is any current in collector terminal, it can pass through the transistor when we apply any input over here. Okay, but when we didn't apply any input over here, this current cannot flow through the transistor and will not be grounded. Okay, so when we apply the input, this current will pass through the transistor and it will be grounded. But if we don't apply any input over here, any input voltage over here, then this current will not pass through the transistor and cannot be grounded. So if we take an output over here, what will happen? We have applied some voltage over here. So it will there will be a current, okay, which have a tendency to flow through the transistor and will be grounded. Okay, there will be a tendency to flow this current like this. But now we haven't applied any input over here. That means we are applying 0 at the input. Okay, so what will be the output? So this current cannot pass through the transistor, so it will pass through this in this direction only when the input is 0. Okay, so we will get a high input at the output terminal. Okay, so when the input is 0, we will get 1 over here. Okay, and when we have applied any input over here, say suppose 5 volt we have applied in base terminals, that's why we are representing it with 1, that means 5 volt. Okay, so now we are applying 5 volt to the base terminal, that means the switch is on. Okay, now this current can pass through the transistor. Now in this case, this current can pass through the transistor and it can be grounded. Okay, so now in this case, what we will get in the output terminal? We will get 0. So with this logic, what we are seeing, that when we are applying 0 at the input terminal, we will get output at 1, and when we are applying 1 to the input terminal, and we will get 0 at the output terminal. So this is the basic concept of NOT gate. So this is how, using this transistor we can easily develop a NOT gate. The same thing happened on the other gate also. So let's take an example of say suppose OR gate, AND gate. Okay, so if we connect two transistors such a way, in this way we have connected two transistors. Okay, now what happened here? Say suppose this is input terminal and this is output terminal, and these are the gates. So when we are applying any input voltage to the base terminal, the transistor will be on, and when we are when we are not applying any input or any voltage at the base terminal, then the transistor will be off. So when we get the output, when both the transistors are on, okay, when both the transistors are on, then only we will get the output. But when any one of the transistor is off, the output will get 0. Okay. So this is the concept of OR gate, AND gate. Okay, that means we have to apply high to the both the inputs. Okay, and in case of AND gate, in case of sorry, this is for AND gate. This is for AND gate, and in case of OR gate, what will happen? We will connect the transistors in parallel connections, like here is a transistor, and we will connect another transistor parallel to this transistor over here, and from here we will get the output. So these are the two transistors are there. So these are the two transistors are there in this diagram. Okay, now when we will get the output, if any one of the transistor is switch on, then only we will get the output. Okay, but here in this case we need both the transistor switch on, so that we can get the output. Okay, so this is how we can easily develop NOT gate, AND gate, OR gate with the help of transistors. Okay, and with the help of transistor we can develop all the other gates also, but it will be more complicated if we are going to discuss all these gates here. We will not get any more time. So let's see the internal circuit diagram of that particular ICs. Okay, then we will move forward to the table to perform the experiments. Thank you. So now we will see the internal diagram of that ICs. Okay, so here is the internal diagram of few ICs. Like this is 7408. Okay, and this is for AND gate. So we have discussed the logic for AND gate. So now here is the internal circuit diagram. So when you get the IC, this is the notch. You need to identify this notch first. Then from this side of this notch, you need to start connecting the calculating the pin number. That pin number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. For all the ICs, you can see the same things will happen, and you need to find out the notch first. Then you need to start calculating the pin numbers from this side. Okay, and for every ICs in pin number 7, you can see here is grounded. In every IC you can see pin number C is ground, and pin number 14 is VCC. You can see here this pin number 14 is VCC. Okay, for all these ICs. And you can see that this is a symbolic representation of AND gate, and pin number 1 is input, pin number 2 is also input, and pin number 3 is output. Pin number 4 is input for another AND gate, pin number 5 is input for another AND gate, and pin number 6 is output. Like this, pin number 8 is the output, 9 and 10 is input for third NAND gate, and for fourth NAND gate, pin number 11 is output, and pin number 13 and 12 is input. Okay, so we have 4 AND gate in a particular IC. Okay, and you can see this same kind of configuration is there for each and every cases. This is the 7432 IC, and this is for OR gate. You can see here the same thing. This is 7400, and this is for NAND gate IC, and here also you can see the same kind of configuration. But in case of NOR gate, it is 7402. You need to remember these things. Only NOR gate IC has the opposite direction of the gates. That means pin number 1 is in output and pin number 2 and 3 is input in case of NOR gate. So this thing you need to remember. All the ICs are same type, but only NOR gate is the opposite. Okay. So let's see a few other ICs, like this is 74X86 XOR gate IC. Here also pin number 1, 2 is input and pin number 3 is output. Pin number 7 is ground. Pin number 14 is VCC. All same case is there. Also for XNOR gate also. Okay. And this is NOT gate, as we know that only one input is there and one output is there in case of NOT gate. So pin number 1 is input and pin number 2 is output. Pin number 3 is input, pin number 4 is output. Pin number 5 is input, pin number 6 is output. And for the other gate also this same thing is there. You need to see the directions only. Okay. So this is it. And then we have a 13 input NAND gate. Okay. So it will have 13 input. Pin number 1 to 7 will be input from this side, and pin number 15 to 10 is the input from this side. Okay. Pin number 9 is the output, and pin number 8 here in this case 16 pin is there. Please remember that one. And pin number 16 is VCC. Pin number 8 is grounded. Okay. So this thing you need to remember separately, though this IC is not used much. Okay. But what is the important thing is that for NOT gate it is one input one output, so there are 6 gates are there inside a NOT gate. And the thing you should remember, for NOR gate the direction of NOR gate is opposite from others gate. Okay, you can remember that one. So this is the internal diagram for each and every ICs whatever we will use. Okay, so you can take a note of this, so that when you perform the experiment it will be more easier to for you to understand the connections. Thank you. So hello, this is the panel where we are going to perform the experiment whatever I am talking about. So now these are the ICs, you can see these are the ICs, and it is already placed in the breadboard. I have told you that how you need to place the ICs on the breadboard. You need to first find out the notch. Okay, like for this case, you can see here this is the notch over here. Okay, so you need to place this IC like this way in the middle of the breadboard, so that both the terminals cannot be shorted. Okay, if you short it then the IC will be burned out. Okay, so that's why this thing please keep it in mind. And this side you can see here, from here we will give the VCC and power supply. So we need to give the plus VCC to pin number 14. So let's quickly give that. So this is plus 5 volt and we will connect it with the pin number 14. So let's make this line as VCC. So I have connected this point, that means this line became VCC. So now we need to connect the VCC with the IC. So if we connect this wire like this way, okay, so I have connected this wire like this way, and we have connected the plus VCC with the pin number 14. And now we need to connect the ground, and this is the ground terminal, and we'll make this line as ground. Okay, so this line became ground. All this line 5 line will become ground now. So if we connect this point to this point, now we have connected the ground to the pin number 7. Okay, this is how the circuit can be built. Okay, and this is a very basic connection. So if you understand these connections, you will be in beneficial position to build a complicated circuit. Okay, now we need to connect the inputs, and we will give the inputs from this terminal. This is the input terminal, as I have already told, and this is the output terminal. Okay, so we need to connect the input. So this is input 1. We need to connect it with pin number 1. And as I can see, this is 7404, the IC number. It may not be clearly shown over here, but the IC number I can see here that it is 7404. That means it's a NOT gate IC, and in case of NOT gate, only one input will be there and one output will be there. So we will not connect this input terminal, rather we will connect the output terminal with the pin number 2. So we will see the output over here. We will observe the output in the output terminal, and we will connect this terminal with pin number 2. So now we have connected this terminal with pin number 2, and like this way we have already completed the connections for verification of the IC. That we now will see that whether the IC will working properly or not. Now we have switch on the device, and all these green lines are the inputs, and for this circuit this is our input terminal. So this will be our input, okay, and it will show the output. So if we give 0 to the input, we can see here the output is high. That means we are giving 0 in the input terminal, and we are achieving output terminal high. So this NOT gate is working properly. So if we change from 0 to 1, the output is also changing from 1 to 0. Okay, you can easily observe that one. That means this IC is working properly. Now you can check all these gates, whatever gate is there inside this IC. Okay, and like this way you can check all this. So we have verified the NOT gate, and now we will take another logic gate, that is this next one. This next one is 7408. 7408. That means this is the IC of AND gate. Okay, 7408. That means AND gate. I will try to show it. The number it is now. You can, if you see minutely, you can see it's 7408. Okay, here it is written 7408. Okay, so it's AND gate IC, and we will quickly verify that whether this IC is working properly or not. So for that, what we need to do, we need to connect the plus VCC first. So this is plus VCC again, and we will make this terminal as VCC terminal, and we will connect the ground also, and we will take this terminal as ground. Let's quickly connect it. Okay, we have connected it, and now we need to give the plus VCC and ground to the IC. So pin number 14, this is pin number 14, and this terminal is for VCC. So we need to connect these two terminals. Now we have given the plus 5 volt to the IC, and we need to connect the ground terminal also. So we have connected the ground terminal. Okay, so we have connected the ground terminal also, and now we will give the input to the IC. So as it is AND gate IC, so pin number 1 and 2 will be pin number 1 and pin number 2 will be the input. So this is input number 1. It should be connected with pin number 1, and this is input 2. So it should be connected with pin number 2. And we will observe the output at the output panel, that is this side. So we need to connect the output terminal with pin number 3, so that we can observe the output. So we have connected that one. So when we are verifying this thing, you need to remember the truth table, so that you can verify that whether the truth table is working properly or not. Now we have connected it. Okay, and now if we switch on the device, you can see when it is 0 0, it should 0, and when it is 1 1, it should 1. Now it's working properly. Okay, so everything is 0. We will work with these two terminals. Okay, these two terminals, these are the inputs for this case. So initially it was 0 0, so the output is 0. Then we will give 0 1, and the output will be 0 again. Then 1 0, the output will be 0, and then 1 1, the output will be high. Now you can see that when it is 1 1 at the input terminal, the output is high. That means this IC is working properly. Okay, you can easily observe by varying these input knobs. Okay, So this is AND gate. Let's take another example where it is it's 7486. This IC is 7486. Okay, so we'll quickly verify this one also. So what is our first step? Let's remove the connections and remove the plus VCC and ground. So we have opened everything. Now we will again connect the whole connection, like we will take this IC. Okay, so we need to give the power supply. For that we need to connect the VCC with pin number 14. So this is pin number 14. 1 2 3 4 5. So we can connect like this way. So now pin number 14 is connected with VCC. Let me switch off the device. And then we need to connect the ground also. So 1 2 3 4 5. So we can connect the ground terminal from here to pin number 7. So we have connected the plus VCC and ground with the IC. Now we need to give the inputs. So as it is 7486, that means 7486 is XOR gate. Okay, so 7486 is XOR gate. So we can connect the inputs, and here also the pin number 1 and pin number 2 will be the input, as it is XOR gate. So pin number 1 will connect the first input with pin number 1, and we will connect the second input with pin number 2, and we will take the output from pin number 3 and we will observe it at the output terminal. So we have connected the IC so that we can easily test the IC. Now let's switch on the device. Okay, and now we can see when it is 0 0, when both the inputs are 0, it is also 0 and this is also 0. So when both the inputs are 0, the output is 0. You can see here the green light is glowing, that means it's 0. Now we need to give 0 1, and when we will give 0 1, the output should be 1. So it's 0 1. You can see the output LED is glowing, it is red now. So that means the output is high for 0 1. So it is obeying the truth table. Now we will give 1 0. Again the output is high, that means it's working fine. And now we'll give 0 0 and the output is low. You can see here it's green now, that means it's 0. So we have easily verified it. Let's see again. So it is 0 0, that means it's green, that means when it is green, that means it's 0, and when it is red, that means it's 1. And it is already green now, that means when it is 0 0, it's 0. Then 0 1, you can see it's glowing, that means 0 1 1. Then 1 0, again 1. Then 1 1, it's 0. That means we have successfully verified the XOR gate also. Okay, so this is how we can verify all the gates. Okay, this is how we can verify all the gates before using the gates or IC for a particular circuit. To build a complicated circuit, you must verify the IC before you used it in practical applications. Okay, so that's it. This is how we can easily verify the all the ICs. Okay, and we can easily observe that whether the IC is working properly or not. So this was the experiment for today's lab. Okay, thank you everyone.